Hello everyone, we are back to continue motion with constant acceleration. In previous video, you remember I explained primary features of constant acceleration motion and also graphs. Now we are gonna extract equations from those graphs. Equations will include velocity time, position time, time independence, and average velocity. Okay, if you are ready, let's start. First, let's consider VT equation. You remember VT graph in constant acceleration must be a line. It starts from V0 as initial velocity and continues as a line. The line, because the slope of this graph is acceleration and acceleration is constant. If you establish a triangle and then attach the hypotenuse of triangle to the line, and if you displace that, the line will have the same slope everywhere. So I can establish a larger one here. And let's continue to the time t, and this is our time interval from 0 to t. And I remember acceleration was delta v over delta t here, okay? So let's write a is equal to delta v over t. Instead of delta t, I use t here because delta t is t minus t naught, and t naught is 0. We started from 0 here, okay? And it's very easy to understand delta v to be at here. So the raise in velocity from here to here will be exactly at. So as the graph gets the velocity of v, we are confident that this velocity will be at larger than v0. So here I can write v is equal to v0 plus at. At is increase or decrease in velocity, and v0 is the initial velocity. Why I said decrease? Because acceleration sometimes is negative. It is not always going to be a positive value. So anyway, it is a change in velocity, increase or decrease. And I should emphasize something more, that as the acceleration is constant and the slope of this line is constant, we are sure that we can write average velocity to be average of the initial and the final velocity. So v0 plus v over 2 will be our average velocity. This is not valid in different types of motion, just in constant acceleration. If VT graph is not a line, you cannot use this equation. And also you cannot use this equation, as the slope of the graph must be constant when I write v is equal to v0 plus at. So these equations are all valid just for constant acceleration. Okay, let's continue for xt. Okay, I'll continue with the same VT graph to extract xt equations. You remember, area under the VT graph is delta x. So if I shade this area and call it delta x, I will find the area of this trapezoid by this method. Delta x is going to be small base plus large base times height over 2. Small base here is v0, so I will write v0 here. Large base is v, so I will substitute v, and then height is t, so it's t. That's all. So delta x is going to be v0 plus v over 2 times t. If I plug in the v here, I will find another alternative for delta x. V, you remember, was v0 plus at from the previous slide. So I can write v0 plus at instead of v. Okay, and then I will write delta x to be 2v0 plus at divided by 2 times t. And if I rearrange the equation, I will find a half of at squared plus v naught t. Some prefer to write delta x like x minus x naught. And so you will have another feature of this equation to be x minus x naught to be a half of at squared plus v naught t. Or if you prefer, you can write it x equals a half of at squared plus v naught t plus x naught. This is not that different. Some prefer to write it like this. Okay, let's continue. Here I have time independent equation. Let's get rid of t. How? You remember acceleration was v minus v naught over t. Let's rearrange the equation by swapping these two. And so I write t equals v minus v naught over a. Why not? And then you remember delta x was v plus v naught over 2. Here is the time to substitute t here, okay? And so the equation will be v plus v naught over 2 times v minus v naught over a. And you remember v minus v naught times v plus v naught is conjugate identity. So it could be v squared minus v naught squared. And so I can write it like that. And then I rearrange the equation to make it like v squared minus v naught squared to be 2a delta x. This is called time independent equation. Why? Because you don't see any time here. It is mostly used in the cases we don't have t and we are not gonna use the time in the solution. So it's maybe a shortcut connecting the velocity and the displacement. Okay, let's put all equations in one page. You remember we found velocity time, v is equal to v naught plus at, and average velocity is exactly the average of the initial and the final velocity. Delta x based on v plus v naught over 2 times t, and the other alternative for xt to be a half of at squared plus v naught t. And then I remind you again, delta x is x minus x naught. X is the final and x naught is the initial position. Finally, the time independence equation, in which you don't see any time. Okay, I will have some problem solution now, and all the problems are going to be solved based on two approaches. First, the graph, and second, the equations. Which one do you prefer is up to you. Just let's start. A particle has an initial velocity of 2 meters per second. Its acceleration is 4. Find the displacement after 10 seconds. Okay. First, graphical approach. You remember velocity time in constant acceleration must be a line starting from initial velocity. Here, initial velocity is given to be 2. So the line will start from 2. Acceleration is positive and it's 4. So the slope of this line will be 4. Let's emphasize slope is 4, okay? And then let's finish the process at t equals 10, the final time, okay? Our delta t seems to be 10 seconds, okay? And you remember, if we have delta v here, raise in velocity, acceleration was delta v over t. So delta v seems to be at, acceleration times time. So you will have a raise of velocity for 40 meters per second. Seems the final velocity to be 42 meters per second. Okay, the displacement is area under the graph. Area under the graph will be a trapezoid. So delta x is going to be the small base, which is 2, plus the large base, which is 42. Here is the large base, 42, and then divided by 2, multiplied by the height, t, 10 seconds. Seems to be 44 over 2 times 10, and it's 220. That's all. So 220 meters, the total displacement. This is the first approach. Second could be based on equations, as you wish. The given data are v naught to be 2 meters per second, acceleration 4, and delta x is wanted. This is our goal, and the time is 10. I'm going to find an equation to embrace all the given data. The best is to find just a single equation using all the data, and then the goal may be one of the parameters I should find. Delta x to be a half of at squared plus v naught t may be the best approach. Then I plug in the values. Acceleration is here 4, time is given to be 10, again time here 10, and the v naught 2 meters per second. That's all. So I plug in the values, and when I do the calculation again, I will get 220 meters. It's up to you which one is better, I don't know, but mostly I prefer the graph because everything we extract from as equations are from the graphs. Okay, let's go to the next one. A driver of a car traveling at 25 meters per second along a road applies brakes. The car comes to a stop in 150 meters with a uniform deceleration. Deceleration mostly is referred to the type of acceleration which slows down the motion. So seems the process is like that. A car here is moving with initial velocity of 225 meters per second. Then it decelerates and slows down and then comes to stop here. and the stopping point is here. So the final velocity is 0, the initial velocity is 25, and this is the total displacement. Acceleration must be negative, because the velocity is to the right, so acceleration must be to the left to slow down the motion. And it takes a time of t. Okay, the first part A, the time the car takes to stop. Okay, first approach, is based on velocity time graph or graph. So I draw the VT graph. The VT graph starts from initial velocity of 25, maybe here, and then it will be a descending line. Descending line because the velocity must come to stop. So it starts from 25, goes to 0. As you see here, the velocity here will be 0. Okay, for part A, the time is my goal. So I have a triangle here. You see, geometrically, this triangle has the area under the graph to be 150, Okay, so I know the area of the triangle. So what should I do here? One side is given and the other side is wanted. So it's very easy to find. Just you should multiply 25 by t divided by 2. Geometrically, it's equal to 150. Finished. So the time will be 12 seconds. This is the first part. Then I continue to the part B. Look at the deceleration of the car. The deceleration of the car is exactly the negative acceleration here. Acceleration must be delta V over delta T, or the slope of this graph, rise over run. The rise is 25, the run is t. Here I found the t to be 12, so I exactly plug in values, and then it's 25 over 12. Must be negative. If you want, also you can convert it to decimal features in 2.1 meters per second squared, as you wish. And part C, the average velocity. Average velocity has two approaches. One of them is average velocity. One of them is V naught plus V over 2. V naught is given to be 25, V is 0, and then divided by 2. Mathematically, it's 12.5 meters per second, but we don't accept it because physically it has 3 significant figures, but the components of this calculation maximum may have just maximum 2 significant figures. So I will round it up to be 13 meters per second. Okay, this is not that important, but anyway, you should know that. You can watch all my videos about measurement. I have explained what the significant figure is and how to calculate this type of fraction. Anyway, okay, and or the other one could be average velocity to be delta x over delta t. Again, 150 over 12. And then as 12 has just maximum 2 significant figures, it's rounded up to 13. Basically, it's 12.5, but I round it up to 13. This is the first approach based on the graph. Second approach will be based on equations. So for the first part, as delta x is given to be 150, I use this equation because the initial velocity is given to be 25, final velocity comes to a stop, so it's 0, time is wanted. So it's very easy. The best equation, I think, this is this one. So I plug in the values and then I get the time to be 12 seconds. For deceleration of the car, you can easily use the velocity time equation. V is equal to AT plus V naught. And then plug in the values. The final velocity is 0, the initial velocity is 25, as you know. And then the time is 12. Acceleration is going to be negative 2.5 meters per second squared. And then here the average velocity is seen. It's initial velocity plus the final velocity over 2. That's all. It's going to be again 12.5, but I round it up to be 13 meters per second. A car has an initial velocity of 5 meters per second. So let's draw a car here with initial velocity of 5 meters per second. After displacement of 20 meters, so let's give a displacement of 20 meters to this car. The velocity becomes 7. Okay, the velocity of the car here, the final velocity is 7 meters per second. It's speeding up motion. Found the acceleration of the car. Okay. First, I use the graphical approach and well, mostly VT approach. So let's draw the VT graph. Initial velocity of the car is 5, so it will be a line starting from 5. But the area under the graph will be the delta x, 20, okay, here. And then finally the velocity will get 7. Something I'm looking for is acceleration. And acceleration, is the slope of this graph. The slope, I should first establish a triangle here, will be rise, 7 minus 5 over run. Run is t. Oh, so it's 2 over t. First, I should find the t. Then I plug in the t and find the acceleration. How to find the t? It's very easy. The area of the trapezoid is given to be 20. So here it will be small base 5, large base 7, divided by 2 times t. T is exactly something I'm looking for. Okay, let's do it. T is 40 over 12, 20 over 6, or 10 over 3 seconds. Now I know the time. Then I should find again the slope. The slope will be rise 2 over run. Now t is 10 over 3. So it will be 6 over 10 or 0.6 meters per second squared. This is the first approach. Second will be based on equations. Which equation is the best to do it once? You know that time was not given. When I read the question, I see time was not given. Good. What should I do? I should use an approach just to get rid of time. So time independent, yes. Time independent equation is something that seems as a shortcut eliminating the time. V squared minus V naught squared is equal to 2a delta x. Final velocity is 7. Initial velocity is 5 and delta x is 20. So the only thing remains is the acceleration. I will do the calculation. I will get the same value, 0.6 meters per second squared. A car brakes suddenly and stops 4 seconds later after traveling a distance of 40 meters. So I have a car. Initial velocity is something I don't know, and then it stops after 4 seconds. 4 seconds. So the final velocity will be 0. And here you will have the delta x of 40 meters. Okay. My first alternative will be VT graph, So let's start. The VT graph will be a line, descending line, of course. It starts from initial velocity of V naught, I don't know, and then it goes to stop after 4 seconds. Here, the area under the graph will be the delta x, 40 meters, here. Now, I can continue with the slope. The slope of the graph will be a, acceleration, something I don't know, and let's continue to find it. Here is very easy. I can manage to find the V naught based on the substitute value of acceleration. Why? Because acceleration is the slope. So it's V naught rise over run over 4. So instead of V naught, we can write 4a. So here I can write 4a. Then I use the area under the graph. Area under the graph is 40. And so it's a triangle. 4a height times base times 4 divided by 2. That's all. So acceleration will be, let's forget about it, 10 will be 20 over 4, so it's 5. But it will be negative 5 meters per second squared because it's a descending line. Acceleration must be negative. So I will write it negative 5 meters per second squared. Find the speed of the car before braking. It's exactly V naught. So the V naught will be 4a. 4a means 4 times 5. So it's 20 meters per second. And finally calculate the speed of the car 1 second before stopping. Let me change the color of the pen to make it visible for you. Okay. 1 second before stopping is t equals 3. I want the speed of the car exactly here. how much the speed is, I will find it. Look at this triangle. This triangle has a slope of 5. 5 is a slope, not the hypotenuse. And the horizontal base is 1, and vertically it's v. That's all. So based on the definition of a slope will be rise over run, v over 1, so the velocity will be 5. That's all. So the velocity 1 second before it stops is 5 meters per second. It's very easy. But the second approach, which is equation. Here I use velocity to be at plus v naught. But I'm looking for acceleration, but I don't know the initial velocity either. What should I do? Okay, let's find an equation to find the initial velocity and then continue to plug in the v naught here to find the acceleration. So the best here will be delta x equals v plus v naught over 2 times t. Because I know the delta x is given to be 40 meters, I know the velocity, final velocity is 0, and the time is given to be 4 seconds. So it's very easy to find. I plug in the values and find the initial velocity to be, let's simplify this, it's 10, 20. Okay, it's 20 meters per second. Then I plug in the 20 here. It's exactly something I found. And then acceleration is gonna be negative 5 meters per second squared. Find the speed of the car before braking. Basically, we did it. And then finally calculate the speed of the car 1 second before stopping. You know, velocity time equation is a generator of velocity. Basically, it's a machine. It gets t from you, and then the output will be velocity. So here, whatever you give as the time, you will get the corresponding velocity at that time. So the best is to plug in the t equals 3 seconds in this equation. So if I plug in the values, negative 5 times 3 plus 20. That's all. So the velocity will be 5 meters per second. This is exactly the velocity 1 second before stop. An object with an initial velocity of 20 meters per second and initial position of negative 75 meters moves at a constant acceleration of negative 20 meters per second squared. Sketch the position time graph for this motion for the first 20 seconds. Okay, let's consider x-t graph from the beginning. You know, x is equal to a half of at squared plus v naught t plus x naught. Basically, it's a polynomial of the second order because t has the exponent of 2. So it must be a parabola, concave up or concave down depending on the sign of acceleration. As the acceleration is negative here, the graph seems to be a parabola with the concave down shape, something like this, or maybe something like this. Okay, so let's do it. First, I write the equation and then I try to draw it based on mathematical approaches. So x is equal to be a half of at squared as the acceleration plus v naught t plus x naught, and as the acceleration is negative 2, you see it's going to be negative t squared plus v naught is 20, so it's 20 t plus x naught is given to be negative 75, so it's negative 75. This is exactly something you see here. Okay, then the next step will be checking the format of the graph. As the acceleration is negative, I told you the graph will be concave down. It starts from negative 75 and it's gonna be something like this or something like this or something like this. The number of passing through the origin here, or exactly when it touches the x-t graph or no touch anymore, depends on the number of roots of this equation, because according to every single root, we will have a touch on t graph. Okay, what should I do here? I should check if we have any root or no. So I will break it into 2 parts. Maybe something like this. Okay, I proved that we will have 2 roots to separate, distinguish roots, but how to do that? I break it into t minus 5 and t minus 15. You know that this equation also could be rewritten as that. Then I put it equal to 0. Okay, every single parenthesis must be equal to 0. So the root from this first root will be 5 and the other root will be 15. So we will have two roots. Means that the object will pass through the origin first at t equals 5 and second at t equals 15. So we will have roots. To complete the graph, we can use another feature of the parabola. You know that parabola is symmetrical over the peak point. So here the peak point will be exactly in between the two roots. So from here to here will be equal to here to here. You know that this is 10. If I divide the 10 by 2, I will get 5 and I will get 5 here. So this point is exactly t equals 10. And then if I plug in the 10 in the equation, I will get the peak point at x equals 25. The object will not continue more than 25. It goes to 25 and then the velocity here will be 0, you know, because there is no slope. Velocity will be 0 and then goes back. So finally it will get 25 and then goes back. That's all. And as it is symmetrical, you know, if I draw the vertical line from the peak point, here and here are equal, will have equal values. So it will be again, you see from here to here, I see exactly 10 seconds. So it will be again 10 seconds to here. So finally it will get negative 75 again meters at t equals 20. Of course, the graph will be continued to infinity, but first part, as for explaining the symmetrical properties of the graph and concaving down and initial velocity and so forth, will be from 0 to 20 seconds. More than that is nothing but extension of the graph to infinity. A ball A starts from the origin moving to the right from rest with a constant acceleration of 2 meters per second squared. So here is the ball A. It starts from rest with acceleration of 2. I will emphasize that the initial velocity of A is 0. Second one is starts 2 seconds later. 2 seconds later, a second ball B, okay, it starts from the same point. Let's say this is the origin, and moving to the right with a constant velocity of 9 meters per second. So it's a constant velocity motion. It's not accelerated. Okay. Determine the positions at which the balls meet. Basically, when they meet, XA is equal to XB. We know that. But we have two different alternatives, you know. First approach will be based on VT graph. Now, this is a mission for you. It's on you. Do it. If you learn how to work with VT graph, do it. Second one is based on the other alternative of me, which is equation. How to do that? I should write the equation of A and the equation of B and then substitute the values to find where they meet. Why? Because when you put XA equals XB, they are at the same location, same position, so they meet because it's a straight line. So for A, XA is gonna be a half of AT squared plus V naught T plus X naught. So they are all 0. That's all. This is for A. And for the B, XB will be VT, so it's 90. But be very careful. The stopwatch registering the time of A or measuring the time of A is indicating TA and the other is indicating TB. They are not synchronized because B starts 2 seconds later. Basically, as B starts 2 seconds later and when they meet, they are at the same position simultaneously. Basically, the total journey for B takes 2 seconds less. Again, I start explaining that. Pay attention. They start from here and then they go to get somewhere to meet. When they meet, they are simultaneously at one point. But for A, it takes TA as the second ball B starts 2 seconds later, it's TB, which is TA minus 2. The total journey for B takes 2 seconds less. So basically for writing the equation of the B, X equals VT, it's 90, but not t, what? tb. Basically, if you want, you can write ta minus 2. Okay, so equation of motion for A will be a half of A ta squared, but for the B, 9 ta minus 2. But if you don't mind, we can forget about ta and ta here and write them as t. 9t minus 2 and a half of at squared. Okay, so it's very important point here in this problem, as the B takes 2 seconds less in its journey. Now I plug in the values, the acceleration, and then I rearrange the equation and then put it equal to 0. It's a quadratic function equal to 0. It will have two roots. The roots are exactly t1 and t2, the time at which the objects meet. I can change the appearance. I can break it into two parentheses like that, t minus 3 and t minus 6, and then if I put every single parenthesis to be equal to 0, it will be 3, the root, and the other will be 6. So I will have t equals 3 and t equals 6 seconds for the two meeting points. They will meet twice. How to find the location of the meeting, position of the meeting? It's very easy. You can plug in the t in each equation. Let's put it in xa, because it's basically ta, And so xa is a half of a t squared, 3 to the power of 2. It's 9 meters. And the other is 6 again. xa is equal to a half of at squared, 6 to the power of 2. Then it's 36. That's all. Can I plug in the values in the second equation? Yes, of course you can, because basically the second equation also includes ta, ta minus 2, so it's okay. But for the B, the stopwatch of the B indicates not 3 and 6 at the meeting point. In the time scale of B, you will read 1 and 4. Why is that? Because time of the B is 2 seconds less. So basically it's 3 minus 2 seconds, and the other will be 6 minus 2 seconds. This is why I write 1 and 4. So based on the time scale of the B, you can also write xb is equal to 9tb. And then also you can substitute tb to be 1 second and 4 seconds, and then get the same, 9 and 36. But it's easier to work with this one, as t minus 2 is exactly tb. If you plug in the ta here and again the ta here, you can directly find the location of b at that moment, or those moments. And basically they will be the same. To continue, I should explain something more. Let's draw x-ray graph to see what happened. For a, actually a is a half of at squared. This is the equation of motion for A. So it's t squared. It's a parabola concave up, starting from the origin. For the B, basically xb is equal to 9 times t minus 2. Okay, because this is the time scale of A. So in that time scale, it will be t minus 2 for B. Here, it cannot start from 0 for the B. You should start it from 2. Mathematically, yes, it can, but physically, no. Because in physics, the time here cannot be negative. So I will start B from t equals 2. And then I continue drawing a line. Why the line? Because B has constant velocity. Okay, they will have two meeting points, t equals 3 and x equals 9, the first meeting point, and the other meeting point t equals 6 and x equals 36. Okay, and this is exactly the event. Look, they start from the same point, first meeting point and second meeting point. Again, look at them. They start from here, B is later, you see, and then they continue, then A accelerates to overtake the B again. That's all. 36. Okay, this was the last problem. You should do more practice, guys, and I'm again thankful to you because of being with me. Don't forget to study hard and review the lesson. See you in the next video.